All right, more simply scheme. I think I left off here where I was reading through how map and filter and reduce work, and so this was going to be the next section. So I'll just take it from there. So, and it's just, this chapter is all about lists, and it's going through selectors and constructors, right, car, cooker, list, cons, append, all that stuff. Sentences are just lists. Right, okay. So, other primitives for lists. Primitives being built-in functions that we can call when dealing with lists, built into Scheme, or this version of Scheme. Oops. We want this simply redef.scm file. That's the version I found on GitHub that actually seems to let me do simply schema exercises with approximately the right output. So the list predicate returns true if its argument is a list, false otherwise. Okay. We see that works. List this true, and list, and then that is false, which is what I would expect. See, I messed up things here because I forgot to put the apostrophe. It's all good. And then, yeah, and then I forgot the question marks. Yeah. Syntax. Syntax is important. Okay. The predicate equal, which we've discovered earlier as applied to words and sentences, also works for structured lists. Oh, okay. So you can check. All right, so you see, we do equal this list of letters and this list of letters. Those are the two arguments, and you get true. But then if I have the same list of letters, but then I take the G out, it says false. Again, what we would expect. The predicate member, which we'll use in one of the examples above, isn't a true scheme primitive, but part of the word and sentence package. You can tell because it takes apart a word to look at its letters separately, something Scheme doesn't ordinarily do. Scheme does have a member primitive without the question mark that's like member except for two differences. Its second argument must be a list, but it can be a structured list. And instead of returning true, it returns the portion of the argument list starting with the element equal to the first argument. This will be clear with an example. Okay, because I barely made it through that. Let's see. Member, no question mark. D, and then this. Oh, portion of the argument list starting with the element. I see. So basically member. That's not how I would name that, I guess. That's okay. Because it's like starting from so if it's not a member, right? So if the first argument is a member, then it sort of takes a snip from that to the end, and then if it's not, it actually returns false. So I would expect this to return basically everything but the G. I've reversed the order just to make it more fun. Yep. All right. This is the main example and scheme of the semi-predicate idea that we mentioned earlier in passing. It doesn't have a question mark in its name because it returns values other than true or false, right? But it works as a predicate because any non-F value is considered true. The only word and sentence functions we haven't already mentioned are item and count. The list equivalent of item is called listRef. It's different in that it counts items from 0 instead of from 1, and it takes its arguments in the other order. Yes, it's 0, 1, 2, 3, and then that's why. So then 0 should be happiness. Yeah. Okay. So the list equivalent of count is length, and it's exactly the same, except it doesn't work on words. Okay. Yeah, straightforward. Association lists. An example earlier in this chapter was about translating from English to French. Yeah, that's what I went through some in the last video. This involves searching for an entry in a list by comparing the first element of each entry with the information we were looking for. A list of names and corresponding values is called an association list or an A-list. So one thing about the ASOC procedure, primitive, whatever. So I did their example. So they say the scheme primitive ASOC looks up a name in a list, but it assumes that there's only, I guess, one like match for it, or maybe that's not quite the way to put it. It only returns the first match. So for George, for the Beatles, their real names, you put in George and you get George Harrison back as the result. If you change John Lennon to George Lennon, though, then that's the result you get back, and you never see George Harrison. So, and then it's only looking up like the first. It checks against the first term, I guess, by comparing the first element of each entry with the information we're looking for. Right? Okay. So it looks at the first element of the entry. So the entry is this, and then it checks the first element, and if you get a match, it returns the whole result, and it only does that for the first match that it gets. I'm sure you could write a program that would, return them all, but ASOC only does the first. So if you reverse, so I took my example with George Lennon, and I inverted the name, so it's Lennon George and Harrison George, and I got back false for that. So I thought it'd be good to compare the earlier implementation of dictionary with this one. So just to understand what difference using ASOC makes. So we see that the first difference is we don't have a lookup here, because the actual, or I should say, we don't have it here. And this on the left is using ASOC, because the actual looking up is done, I guess with the ASOC primitive. So that's not something that we have to directly worry about. So in this new implementation on the left here, we just define the dictionary as the first step, as a list. And then, so it gets more interesting when we get to the second part of it. So you'll notice on the right here, we did like a check to see if the dictionary was empty. Because if you remember like how this worked, like basically, we had this procedure, look at the first value in an entry in the dictionary and see if it matched our word. This is the equal thing. And then if it did, then we'd return the second part of it, the translation, the French translation. And if not, then we do a recursive call and look at the next, go to the next entry and basically do that one by one. But we don't have to do that on the left because basically the ASOC is handling that whole process of like looking through the list, of going through it, of stepping through it, like entry by entry. So we've sort of abstracted away that part of it, so we don't need to worry about that. But we still need to worry about something. So what we're doing here essentially is, so we say let record ASOC word dictionary, which is basically let is basically, and I did quickly look this up, but I think I got the idea pretty quickly, is basically saying let this, which is a variable, equal the result of this, and then we're going to use that going forward to figure, to perform this this computation here. So now what is this? So ASOC word dictionary is just basically what we were doing before with the Beatles, ASOC, and then we give it a word, and then it looks for and tries to find the first entry it can, where the first element of the entry is the word that we've given it. Now, this if record is sort of similar to this null dictionary, not quite, like the way, because the actual program, the way it works is kind of different, but it's serving a similar role in that, like, it's what happens if, or I should say, if we return false on this, then we go to this. Whereas if we null was a little different, because if we returned true on that, then we would output the do you speak English? I think parlez-vous, right? Do you speak? But if there is a record, so this message is the failsafe, but if there is a record, then we return the second element in the list that is the record. So, right. ASOC returns false if it can't find the entry you're looking for in your association list. Our translate procedure checks for that possibility, if record, right? That's what it's doing. Before using cater to extract a French translation, which is the second element of an entry. Functions that take variable numbers of arguments. In the beginning of this book, we told you about some scheme procedures that can take any number of arguments. But you haven't yet learned how to write such procedures for yourself, because Scheme's mechanism for writing these procedures requires the use of lists. Here's a procedure that takes one or more arguments and one or more numbers as arguments and returns true if these numbers are in increasing order. So define increasing number. Increasing number, rest of numbers. There's a dot there. Cond. Null, rest of numbers true. The first novelty to notice in this program is that the dot is the dot in the first line. In listing the formal parameters of a procedure, you can use a dot just before the last parameter to mean that the parameter, rest of numbers in this case, represents any number of arguments, including 0. The value that will be associated with this parameter when the procedure is invoked will be a list of elements, a list whose elements are the actual argument values. In this case, in this example, you must invoke increasing with at least one argument, that argument that will be associated with the parameter number. If there are no more arguments, rest of numbers will be the empty list. But if there are more arguments, rest of numbers will be a list of their values. In fact, the two cases are the same. Rest of numbers will be a list of all the remaining arguments, and if there are no such arguments, rest of numbers is a list with no elements. So I guess this is just saying rest of numbers will be a list of all remaining arguments if there are any. And like a list, if there are no such arguments, rest of numbers is a list with no elements, which is all the remaining arguments because there are none left. So that's almost like a semantic point, but that's okay. The other novelty in this example is the procedure apply. It takes two arguments, a procedure and a list. Apply invokes the given procedure with the elements of the given list as its arguments and returns whatever value the procedure returns. So apply invokes the given procedure with the elements of the given list as its arguments, right? So given procedure, elements of the list, and returns whatever value the procedure returns. Therefore, the two following expressions are equivalent, right? Because this would just add up all of them. Yeah. And this will do the same. We use apply and increasing because we don't know how many arguments we'll need in the recursive invocation. I see. So you can't specify like, right. We can't just say increasing rest of numbers because that would give increasing as a list, because that would give increasing a list as its single argument. It doesn't take lists as arguments, it takes numbers. We've used the name rest of numbers as a formal parameter to suggest the rest of the arguments, but that's not just an idea we made up. A parameter that follows a dot and therefore represents a variable number of argument is called a rest parameter. Here's a table showing the values of number and the rest of numbers in the recursive invocations of increasing, for example. Before I look at this, just to take a step back. So I did trace on increasing and greater than, just to see better what was going on inside the procedure. So basically, so I made a test program for myself because I wasn't actually fully grokking the dot. So it really, like I was looking at this and I was like, wait, why don't, because with recursive calls, I'm used to having, and when you're like going through a list of things, I'm used to having to like call, like specify the like the first thing and then the rest of it. But I wasn't quite grokking that like this is what's doing that. Like you can, whatever number of, like it says here, but I didn't, let's reread. whatever, got interrupted there. Whatever number of things that you give before the, whatever number of formal parameters, things that you give before the dot, it's gonna peel those off of the total like list you're feeding it and deal with those separately, and then you'll have the rest. So you see here I did my program was called testing, and I did number 1, number 2, dot, and the rest. And so I just did very simple. I just displayed number 1 and number 2 on new lines, and then on their own lines, and then the rest on another line. And yeah, so you could see like this list, this 12 got peeled off as number 1, 4 got peeled off as number 2, and then the rest of the list, which is the rest, got put on its own line as a list. So yeah, I wasn't really grokking the dot and like how it actually worked. But now that I figured that out, I can see with each recursive call here, you're going to be peeling off that first number before the dot. And then it's going to go through the whole rest of the analysis. And so let's do that. All right, so you can see what I did here. Increasing, and then I put in some numbers, and I'm doing trace on increasing and greater than, just so you can see the flow of the program a little more. So at each step of call or recursive call in the increasing function, we wind up comparing two numbers. I'm going to talk about this first because, even though this line is first, it kind of comes like this line and this line, I think, kind of come last in a way, like conceptually. So the thing about recursive calls is like the order of the program is not necessarily the order of the best way to think about it. So we have number and rest of numbers. So we go through this program and we see, okay, is the car of rest of numbers, which is going to be the first of that list, is that greater than the number? So like the first number. So for this list, number would be 1. Rest of numbers would be this stuff, 3, 5, 8, 11, 14. And the car of rest of numbers would be 3. So we'd be saying, okay, is 3 greater than 1? And 3 is. So then we say, okay, so then apply, so if that's the case, apply increasing to rest of numbers. This is a recursive call. Now, another thing I was confused about. Right, so one of the things I found confusing was, so this says we use apply and increasing because we don't know how many arguments we'll need in its recursive indication. We can't just say increasing rest of numbers because that would give increasing a list as its single argument. And it doesn't take lists as arguments, it takes numbers. Right, so to get this down to very fine detail, I actually broke increasing and I gave it, I took the apply away. And what I discovered was that, where is it? There we go. So So if you give it like 1384, which should return false based on what we want the program to do, because 4 is not higher than 8, so that breaks the pattern that it returns true for. It starts off okay, like the first step is okay. It says okay, compares 3 and 1, that's fine. But then when it does the recursive call, it passes the remaining numbers as a list, like as a unit, a list object. And I think what's happening is because at that point, rest of numbers is null because there's nothing there, so it's like the empty list. Because everything is now in the first argument, like everything is number. Even though there's 3 of them, but it's in a list. So then rest of numbers is empty. And so when this null check happens, null rest of numbers, it comes out as true. And so the whole thing returns as true, even though it's not. So that shows you some of the necessity of apply here. Because it does not, because you have to be precise. You want a list of numbers, but not in like a scheme list object. You want them like, you want it like this, like with no parens around them, if, to put it one way. So then, as the program is written though, so, you pass in the list, it pulls off the first number, checks that the rest of the numbers isn't empty. If it is, it returns true. If it's not, it does this stuff. It takes the first number of rest of numbers, makes sure that it's bigger than number because it's supposed to be increasing. And then it does the recursive call. And so this is what catches it if it's not increasing, because if, like in my, well, I don't have it any, but okay, yeah. And if you go from like 12 to 4, it's going to say, well, it's going to return false for 4 greater than 12. So then you return false, and then that's it. And the increase, okay, so now we can read this table. Here's a table showing the values of number and rest of numbers and the recursive invocations of increasing for the example, this example. Right. So you see one's getting pulled off, at each level, and then it returns false because 6 is not greater than 20. In the increasing example, we've used one formal parameter before the dot, but you may use any number of such parameters, including 0. The number of formal parameters before the dot determines the minimum number of arguments that must be used when your procedure is invoked. There can only be one formal parameter after the dot. So a recursion on arbitrary structured list. Let's pretend we store this entire book in a gigantic scheme list structure. It's a list of chapters. Each chapter is a list of sections. Each section is a list of paragraphs. Each paragraph is a list of sentences, which are themselves lists of words. Now we want to know how many times the word mathematicians appears in the book. We could do it this incredibly boring way. So the book says this is boring, and I'm going to kind of take its word for it, but I think what's going on is basically doing length. You're doing length on the list of words that match the given word in a particular sentence. So that produces a number, like, so that's what length does, is it gives you a number. And then these are just like adding up those numbers, and there's just like a layer of function for each layer of the scheme list structure, I think. So I don't know how worth it is to puzzle that out in detail, so I'm just gonna like take, like I said, take their word for it a little bit. It would be incredibly boring. Okay. What we're going to do is similar to the reasoning we used to develop the idea of recursion in chapter 11. There we wrote a family of procedures called down, up 1, down, up 2, and so on. I vaguely remember this because I did get through the recursion stuff at least. When I did this last time, we then noticed most procedures looked almost identical and collapsed them into a single recursive procedure. The same spirit. Notice that all the appearances in procedures are very similar. We can make them even more similar by rewriting the last one. So in this deep appearances program that they've written, reduce is gonna add up. Like reduce operates, it takes, say, the first two operators and does procedure on them, and then takes the result of that and does it on the next argument, I guess, rather, and so on. So it'll basically add up all the numbers that result from this. Map is going to apply this, or yes. All right, I see they explain some more here, so let me back up a little bit. So what's the base case? Books, chapters, sections, paragraphs, and lists are all lists of smaller units. It's only when we get down to individual words that we have to do something different. So you have the name of the function, word, and then whatever list structure you're passing it. If the second argument is a word, then you check if the word and the second argument are equal. If they are, you return a 1 because you're trying to count, and if not, you return a 0. And then there's this recursive call, and this part I don't fully understand, but let's see. So oops, gotta run it. Right, so well, you know what I forgot to do is there we go. Maybe that took a while. Okay, so that's some output. So this is quite different from the recursive situations we've seen before. What looks like a recursive call from deep appearances to itself is actually an anonymous procedure that will be called repeatedly by map. I think by deep appearances doesn't just call itself once in the recursive case, it uses map to call itself for each element of structure. Each of those calls returns a number, map returns a list of those numbers. What we want is the sum of those numbers, and that's what reduce will give us. Right, so basically, it took me a while to read this, or to think about it. So this is a unnamed procedure which makes a recursive call to deep appearances. And it's structured in this way because we want the recursive call to the procedure to be made to every element of the structure. So we don't want to, we basically want something that's going to keep sort of digging through the layers of the structure until it hits the base case. And so we want this map in order to make sure that we're hitting each level of the structure of the nested list with this procedure. And then, it's a recursive call. So then if it has its own nested structure, it'll also get mapped through, and every element will get, processed and, go through this procedure and so on and so on and so on, even if it's a huge, massive thing. So I sort of have, let's see what they say, because I'm not like super clear on this. I have the general idea. So this is actually quite different, or this is quite different from the recursive situations we've seen before. What looks like a recursive call from deep appearances to itself is actually inside an anonymous procedure that will be called repeatedly by map. Deep appearances doesn't just call itself once in a recursive case. It uses map to call itself for each element of structure, right? And so instead of like, what were we doing before? Right. So this was a little weird because it was with apply. But it was still pretty straightforward. It was like, you had number and rest of numbers, and then you do the test for if it's greater, and then you call this with rest of numbers, and that's one call, and then you go in it again. You do the recursion, and you do the analysis again, and so on. And it's very sort of linear and straightforward, and that was represented by this table where you see number and rest of numbers is one number and what is this 6 rest of numbers, one number and 5, one number and 4 rest of numbers, one number and 3 rest of numbers, and so on, right? Whereas with this, we're sort of spawning a series of recursive calls at each layer of the structure. We're sort of, if you think of almost like, I don't know, like digging machines or something, we're like, okay, this level of the list structure has 10 elements, let's make 10 digging machines. And then, those go down. And then if one of the digging machines finds that there's 5 elements to the sub list structure, then it spawns 5 more, and those go down, and so on and so on. And then we count up all the digging machines at the end. I mean, that's a very loose metaphor, but so each of those calls are returned. Okay. So deep appearances doesn't just call itself once in the recursive case. It uses map to call itself for each element of structure. Each of those calls returns a number. Map returns a list of those numbers. Right. Map returns a list, which, returns a bunch of ones, basically, I think. Yeah. You can see, you can see here when the and the match, when the word and the structure word or whatever match, the second argument, then we get 1 back. And when not, we get 0 back. And then we add up the ones at some point. We get 2, and then we get 3, and then we return 3. And that's what reduce does at the higher level of the, like after all the digging is done, then reduce adds up all the ones and gives us whatever number it is. So this explains why deep appearances must accept words as well as lists as the structure argument. Consider a case like deep appearances foo IB. Since structure has 2 elements, map will call deep appearances twice. One of these calls uses the list A as the second argument, but the other call uses the word B as the second argument. So, of course, if structure is a word, we can't make recursive calls for its elements. That's why words are the base case for this recursion. What should deep appearances return for a word? If it's the word we're looking for, that counts as 1 appearance. If not, it counts as no appearance. You're accustomed to seeing the empty list as the base case in a recursive list processing procedure. Also, you're accustomed to thinking of the base case as the end of a complete problem. You've gone through all the elements of the list, and there are no more elements to find. In most problems, there's only 1 recursive invocation that turns out to be the base case. But in using deep appearances, there are many invocations for base case. 1 for every word in the list structure. Reaching a base case doesn't mean that we've reached the end of the structure. You might want to trace a short example to help you understand the sequence of events. Although there's no official name for a structure made of lists, there's a common convention for naming procedures that deal with these structures. That's why we've called this procedure deep appearances. The word deep indicates that the procedure is just like a procedure to look for the number of appearances of a word in a list, except that it looks all the way down into the sublists, instead of just looking at the elements of the top-level list. This version of deep appearances, in which high-order procedures are used to deal with the sublists of a list, is a common programming style. But for some problems, there's another way to organize the same basic program without high-order procedures. This other organization leads to very compact but rather tricky programs. And it's also a widely used style, so we want you to be able to recognize it. Here's the idea. We deal with the base case words just as before. But for lists, we do what we often do in trying to simplify a list problem. We divide a list into its first element, its car, and the rest of elements, its cdr. But in this case, a resulting program is a little tricky. Ordinarily, a recursive procedure for lists makes a recursive call for the cdr, which is a list of the same kind as the whole argument, but does something non-recursive for the car, which is just one element of that list. This time, the car of the kind of structured lists of lists we're exploring may itself be a list of lists. So we make a recursive call for it as well. Oh yeah, I've seen this type of. Right, so this procedure has 2 different kinds of base case. The first 2 con clauses are similar to the base case in the previous version of deep appearances. They deal with a structure consisting of a single word. If the structure is the word we're looking for, then the word appears once in it. If the structure is some other word, then the word appears 0 times. The third clause is more like the base case of an ordinary list recursion. It deals with an empty list, say null, in which case, because an empty list would return true for null, in which case the word appears 0 times in it. This still may not be the end of the entire structure used as the argument of the top-level invocation, but may instead be this may instead be merely the end result of, or the end of the sublist within that structure. Wait. So this still may not be the end of the entire structure used as the argument to the top level invocation, but may instead be merely the end of a sublist within that structure. Okay. May instead be merely. That's but may merely be might have been better. Okay. If we reach the else clause, then the structure is neither a word nor an empty list. Right, because we've checked for those. It must therefore be a non-empty list with a car and a cutter. Makes sense. Right. Even if it has one element, I'll still have a car. Or wait. Right, if you cutter a one element list, you get an empty list. So in deep appearances, the desired result is a single number. What if we want to build a new list of list structure? Having used car and cutter to disassemble a structure, we can use const to build a new one. For example, we can translate our entire book into Pig Latin. Oh, I see. So basically, when you hit a word, you call Pig Latin on the word. So one thing I was wondering with this is how does I made a simple example, or is it? Yeah, foobar. So like I have a couple of examples actually. Let me make this bare. So like if you because I noticed that this was like already nested that a little bit, like this wasn't just one level deep. And I was like, well, suppose we just give it like a word. We give deep piggle a word. What happens? And it returns just a word. It's not in the list structure. So that's interesting. So what if we give it a word that's one level? So we give it a list. One of the elements is one level, and it's on the list's first level, so to speak, and one is on the list's second level. And so it for that it returns a list with the same structure. So I was wondering, so how does that work exactly? And I realized I was thinking of like this is kind of the key, because I was thinking of it like going through the elements of the list or something, and it's sort of a vague thought. But like when it's first sort of when you first pass it, so we've got foobar here, right? When we first pass it this structure, because that's what it's going to be, this structure, it's in a list form. It has to sort of, crack open the structure to actually look at the elements. So when it runs this cons check, is structure a word, it's going to fail. It's going to return false because structure is not a word. And so that happens. That's hard to see though in the trace, but basically that happens, and then you get deep piggle car structure, and so car is going to pull in the foo just as a word, and then foo will pass that test in the recursive call of being a word, and then it'll get turned from foo into ufe. And that So you pass the original, the foobar list into the structure. It's not a word, so it fails. It's not null, so it goes through that check. It doesn't return an empty list. So then we go to the else. And then the reason I'm saying all that again is because I want to emphasize a different thing, which is then we're consing the results of the recursive call. So that's what puts it into the list. See, with the depiggle on just hat, we deal with that at the first instance of the program with no recursive calls. So that's why it's not in a list, because it never gets constant anything. But once you're already dealing with a list, the very fact that you have to look in, the thing which looks inside the structure is always const, basically. Like the recursive call, which is, the sort of the digging machine that's looking into the structure, is always inside this const. So I think I'm crystal clear on that. Maybe. All right. So the book suggests we compare depiggle with an every pattern list recursion, such as praise on over here. So let me see. We did this. I think this was in the last video, because yeah, this is the same. Okay. Right. So kind of similar in some ways. Cons, praise. Both look like cons something, car argument, something, coulda argument, right? And yet these procedures are profoundly different. Praise is a simple left to right walk through the elements of a sequence. Depiggle dives in and out of sublists. The difference is a result of the fact that praised is one recursive call for the coulda, right? Right, one recursive call. While depiggle does two, one for the car and the coulda. The pattern exhibited by depiggle is called car coulda recursion. Another name for it is tree recursion, for a reason we'll see in the next chapter. And that's a reference to the reason I'm reading this chapter. And yeah, I know that it seemed like it was closely connected to the tree recursion stuff, which is what I'm looking at Simply Scheme for help with. Just as we mentioned about names, word, and sentence, resist the temptation to use list as a formal parameter. We used LST instead, but their alternatives are capital L or SICP for sequence. The list constructor does not treat its two arguments equivalently. The second one must be the list you're trying to extend. There is no equally easy way to extend a list on the right, although you can put the new element in a one element list and use append. I'm sorry, I might not have said the list constructor cons does not treat its two arguments equivalently. If you get arguments backward, you're likely to get funny looking results that aren't lists with these dot things. Yeah. Yeah, I looked at this a little bit earlier, I think, in the last video. So I was curious about the dot. The result you get when you con something that isn't a list is called a pair. It's sometimes called a dotted pair because of what it looks like when printed. It's just a printed representation that's dotted. However, the dot isn't part of the pair any more than the parentheses around a list or elements of the list. Lists are made of pairs. That's why cons can construct lists. But we're not going to talk about pairs that aren't pairs of part of lists. You don't have to think about them at all, except to know that if dots appear in your results, you're consing backward. Don't get confused between lists and sentences. Sentences have no internal structure. The good aspect of this is it's hard to make mistakes about building the structure, but the bad aspect is that you might need a structure. You can have lists whose elements are sentences, but it's confusing. You You can have lists whose elements are sentences, but it's confusing if you think of the same structure sometimes as a list and sometimes as a sentence. In reading someone else's program, it's easy not to notice that a procedure is making 2 recursive calls instead of 1. If you notice only the recursive call for the coder, you might think you're looking at sequential recursion. If you're writing a procedure whose argument is a list of lists, it may feel funny to let it also accept a word as the argument value. People therefore sometimes insist on a list as the argument, leading to an overly complicated base case. If your base case test says word, car, structure, then think about whether you'd have a better organized program if the base case were a word structure. Remember that in deep recursion, you may need 2 base cases, one for reaching an element that isn't a sublist, and the other for an empty list with no elements at all. Don't forget the empty list base case. Okay. You got some exercises. So I looked a bit at the boring exercises, 17.1, and they were mostly boring. Got a little spun around on this, just the 3 levels of caricature, but it wasn't too hard. And then this USOC actually was just basically what I did earlier, where I tested what happened with the Beatles if you tried to find like a last name or something, the second value of the pair, and you just get false. So it's pretty straightforward. So 17.2 actually looks more interesting though. So for each of the following examples, write a procedure of 2 arguments that, when applied to the sample arguments, returns the sample result. Your procedures may not include any quoted data. All right, so I got through 17.2 exercises, and then I did 17.3. I just put in the expression and to see what it did. I did procedure. So I'm a little confused about that. Getting a little tired though, so I think I'll wrap up the video here.